Hello, everybody. How are we doing? Can you hear me? Do I sound good? Does my apartment look different from the 6 months or so it's been since we've done this? Well, it looks good on my end. So, all right. So, hi everyone. Welcome back. My name is Danny. I write the newsletter for the club, and I also do this when something like the museum can't hold us, then we have to do these through Zoom. So that's me. We have a great presentation for you tonight. Dr. Lou Mayo is with us to give us a talk about the sun, heliophysics. I was assured that there is at least one slide about the solar eclipse. So get ready. Um, Usually for these things, Chuck is either here or he plays a video. Chuck is in London. I'm pretty sure he's buying a soccer team. Sorry, a football team. Um, so no Chuck either in person or in a weird video. So sorry about that, but it's me and Eileen is here through Zoom. She has some stuff to tell y'all, as well as she will be introducing our speaker in just a minute. I am going to go over some announcements. First of all, I want to apologize to everyone for last month, we found out at like 4:45 p.m. that the museum was unworkable, so we scrambled, and it was a spur of the minute thing. But it wasn't great. It wasn't great. We one of our speakers drove in from Tulsa, and we didn't get to him in time. So Rod, again, I'm so sorry that happened, and let's hope we don't ever have to go through that ever again. Okay, so club business. If you are new to the club, and you want to know where you can go to see some cool stuff, then you will want to go to one of our member nights. We have a private observatory called Cheddar Ranch that is about an hour. That's about an hour and a half outside of the metro area. The dates for that is there's one tomorrow, but I think it's gonna be rainy and cloudy, so I wouldn't plan on that one. But we have another one next Saturday, so if you are interested in going out to that, which I highly recommend that you do if you are new to the night sky, or you just want to go someplace dark and look at some specific stuff, CRO, as we call it, is a great place. And towards the end of the meeting, I'm going to go over how you find all of this stuff and how you know where you're going and all that sort of thing. So, though, also in June, and is a star party called Sally's Night. That is on June the 17th. That is going to be, I believe, in the parking lot of the Science Museum. So, hey, next week you're in the area, or you just want to see some cool stuff, come on by. We'll have some stuff set up there for you to look at. Yeah, it should be a great time. That is June the 17th. I don't know what day of the week that is. Is that like Friday? That's Saturday. So that might be the same day as the member night. So you might have to pick. So I'm not going to tell you which one that you should go to, but you may have to pick. If you are looking for a volunteer opportunity, as well as some stargazing, then our yearly Camp Clap Hands program currently is going on. This is super great. We've been doing this for about 6 or 7 years. Hopefully someone in the chat, like Gerald there, I think, has been to all of them. But yeah, so it's at the JD McCarty Center down in Norman. It's a group of special needs children, and they want to look at space too. So during June and July each year, it's turned into, we go down there on the Mondays, and we set up some telescopes and a projection screen and all that sort of stuff for all these kids, and it really is a great thing. I'm really glad that we do this, and we always could use some more people to just have telescopes, or with laser pointers, or just some knowledge. That's great. So the dates for June of that are June 12th, June 19th, and June the 26th. So if you are interested, if you live in Norman, then that is definitely something that you want to keep your eye on. It's just a great volunteer opportunity. And the kids are wonderful. They go to bed early, so you're not out super late. It's great. Though right now the sun doesn't set till 9 p.m. So I don't know how that works, but whatever. And the last thing I have on my sheet for announcements, as always, is we have to plug the Okitex. So the Okitex Star Party is our big event of the year. This year's a pretty big year too. It is it is a 9-day star party out in the panhandle of Oklahoma, some of the darkest skies that you can see. And that's just not just for Oklahoma. That's like as dark as you can get. It's a great time. Nine days, but you're not roughing it. We've got bathrooms and Wi-Fi and catered meals, and everybody is super nice. So if you need a vacation in September, go to Okitex. And if you are an astrophotographer, then be sure to sign up for the imaging session while you are at it. That is a 2-day add-on to Okitex, but we've got some real pro level astrophotographers that come and give presentations, and it's a 2-day thing. It's a whole thing, so you can learn just all sorts of great stuff. Okay, that's all the announcements that I have, so why don't you quit listening to me and let's listen to Eileen. Eileen, how are you doing?
Give you some information. First of all, for everyone, our next meeting is on Friday, July 14th at 7 o'clock. We are supposed to be at the Science Museum of Oklahoma. I haven't seen if there's a concert scheduled or not, but it is Bastille Day, so we'll celebrate in our own way. Our speakers from May are being moved to July, and that's Rod Gallagher and Mike Mitchell and Brad Ferguson. They will be speaking on scientific data gathering in amateur astronomy. So again, this was the talk that was supposed to have been presented in May when Oklahoma severe weather and a concert at the zoo overflowed and took over the SMO parking lot. So thank you for your patience. On Friday, August 11th at 7 o'clock, we are supposed to also meet at the SMO. Our speaker is Andy Freihofer, and his topic is to be determined, but it is about astrophotography in general, and he is going to be presenting. We're kind of his guinea pigs before the meeting before Okitex. Because Okitex starts on Friday, September 8th, I have been assured by Chuck and other people who cannot make it out to Okitex that we will have a meeting that night. And we've asked the SMO staff for a planetarium show. And so the topic will be determined. And I'm trying to see right now for October if my original July speakers can do it or possibly speak at another time. In November, we are hoping to have Larry Beatty and some of the Dome Boys speak about their trip to Australia, the Australian outback, to do astronomy. They went a few years ago to the big party, and so they would like to share that information with everyone else. So with that, and then the next time we do have a conflict is going to be December, because the museum has it rented out, and we just have to wait and get closer and see. But because since I've been program chair, there have been 2 months, we always seem to have to find another spot, and it's been June and December. So if any of you have any ideas of where else we can do our meetings in those particular months as a backup, please send me an email and as program chair, or post it on the discussion board, because it would be nice that we don't have to scramble, especially at the last minute. May was a whole other ballgame. So tonight, I would like to introduce you to someone that I was introduced to in in June of 2018. Dr. Lou Mayo is a planetary scientist with over 40 years experience supporting NASA planetary research, space missions, space science data centers. He's currently the chief scientist for Gamma 1 Technologies, and he's a professor of astronomy at Marymount University. He's also president of Ares Scientific, which is a small, not-for-profit organization dedicated to astronomy education. His primary research interests have been in understanding the atmosphere of Titan, which is Saturn's largest moon, in developing radiative transfer models of aerosols and molecular species in Titan's atmosphere. He's also, and how I got to know him is he's very heavily involved in astronomy outreach and public communications. For over a decade, he led NASA's team to bring heliophysics mission science and discovery to the country. And that included both Venus transits and the 2017 solar eclipse across America. For NASA's Science Mission Directorate over the last 20 years, he has spearheaded astronomy education programs for Girl Scouts, which is where I met him and try to Zoom with him monthly as we meet some of our Girl Scout astronomy clubs throughout the country remotely. He works with amateur astronomers, university professors, and K through 12 educators. He's currently featured on the YouTube show Space Oddities, which streams every Monday at 3 p.m. and that's Eastern Daylight Time. So that would be 2 p.m. if you are in Oklahoma. His research in professional observing has been involved to acquire infrared spectra from the Voyager IRIS instrument. And these observations have provided insight into molecular species, aerosols, thermal structure, and the dynamics of Titan's atmosphere. From these observations, our understanding of physics and laboratory measurements, model atmospheres can be constructed to mimic what the heck is going on in Titan's lower atmosphere. As an amateur, he has a number of backyard telescopes that he likes to observe with, including an 18-inch f5 star splitter Dob and a 5-inch Explorer Scientific ED APO. Currently, he is building his own roll-off roof observatory in his very own backyard that should see first light in the next few weeks. He enjoys holding star parties for the community and his undergraduate students, and he often travels to see eclipses, transits, and other celestial events. So without any other further ado, I give you Dr. Lou Mayo, and you can put your questions in the chat, and Danny and I will be monitoring that too. Thank you.
Well, thanks, Eileen. That was a very nice introduction, and thanks so much for inviting me to your club. And I love giving talks to the public, and especially amateur astronomers. For a number of years, I was kind of a liaison to the amateur astronomy community, all the way back to, for NASA, all the way back to the Amateur Astronomer Space Telescope. I don't know if any of you are aware of that, but there was an effort through the Astronomical League to put a telescope in space off of the ISS, and it didn't quite work. But so I love amateur astronomy, and of course, astronomy is my passion. So tonight, we're going to talk about the sun. Seems like today we should talk about the sun, but tonight we're going to talk about the sun. And just a few announcements. The first is that in October, we begin NASA's International Year of Heliophysics. This is being keyed off of the October annular solar eclipse, right? And it'll last for a year, and you're going to be seeing a lot of PR, a lot of talks, a lot of programs about the sun and about solar missions during that year from NASA and from other groups. The other is, as many of you probably know, we're getting darn close to solar maximum, right? So solar maximum, it's a little hard to predict, but probably in 2025, we'll have the peak of the sunspot cycle. Sometimes there are two peaks. And so we're seeing more and more sunspots, more and more solar storms, more and more aurora as the weeks and months roll on to 2025. So I guess I can say I'm a veteran eclipse chaser because I've seen one. I've tried to see a few, but I've only seen one. And for NASA, we used to make, I think we still do, these solar viewing glasses. So I have heliophysics observing glasses. I've got these are from the transit of Venus in 2012. These were just ones we made that we thought kids would like to draw on, color their own. And these were from the Eclipse Mega Movie that was a partnership between Google and I think Stanford University. Anyhow, so I like eclipses too. That's my point. And I've got one eclipse slide for you. So let's get started here. Let's see if I can share my screen. Let's hope it works. Can you all see that? Okay. Okay. Through the eyes of NASA. This was a term that Jim Green promoted when he was chief scientist. I guess when he was head of planetary science at NASA. He then became the chief scientist. And so our mantra has been through the eyes of NASA to the hearts and minds of the nation. And so that's kind of what we try to keep in mind as we share the exciting discoveries that have been made in space. Okay, there's my slide. I have one slide today. It's the sun. There it is. There's the sun. Probably that's what most people think of as the sun, right? The sun is 93 million miles, or about 149 million kilometers away. And I may be using different yardsticks in this presentation, all right? If we use miles and kilometers, feet, these numbers get too large. So we're going to use the AU, the astronomical unit, as our benchmark. So you'll hear me talk about the AU, that's the average distance between Earth and the sun. It's just another sized yardstick, just like the light year. You all know what a light year is, right? Yeah, it's just like a regular year, only it's less filling. It's less filling because it's a light year. Okay, so let's move on to the next slide here. There's the sun, as you might see with your backyard telescope, with a good what we call white light or neutral density solar filter. And here we can start to see some features of the sun. We see sunspots, of course. And here in this image, you can see structure in the sunspots. They have shape. They generally occur in pairs. And you can see that there's a dark and a lighter outer region. That dark region is called the umbra. The lighter outer region is called the penumbra, just like the regions that we know about in eclipses. You also might notice that the edges of the sun are darker than the center. And it's a real effect. That's called limb darkening. And that happens as a function of the optical depth changing as you move towards more rarefied parts of the sun. Remember, the sun's just a big ball of gas. It's not a solid body. And so as you move away from the center, you're seeing through less and less gas, and you're seeing darker and darker features. Here's a picture of the sun as was viewed by Galileo in 1611 when he took his 2-inch telescope and looked at the sun. I don't recommend this, by the way, unless you use a solar filter. And he saw sunspots. And this was remarkable because the thinking up to that point was that the sun and the celestial sphere are perfect. They are pristine. They are the realm of gods, not the realm of the unwashed masses down here on Earth. And so the church fought back and said, no, those must be closely orbiting planets. But Galileo proved that those were indeed sunspots because as they rotate around the sun, they start appearing thinner and thinner as they move toward the edge of the sun. which is something that you wouldn't have if they were just planets. Here are some more pictures of the sun in X-ray, ultraviolet, white light, infrared, and radio, and so on. And what I like to say is the universe looks very different depending on the wavelength of light that you're viewing it in. An X-ray universe looks very different than an infrared universe, which looks very different than a radio universe. And one of the differences, I mean, these are different colors. Obviously, we don't see in the X-ray, so that's a made-up color. UV is a made-up color, but it's the structure that we're looking at here. And so you can see that the structure of the sun looks different in different wavelengths, and that is in part due to the fact that we're sampling different depths into the sun's atmosphere, seeing different temperatures at different heights in the sun's atmosphere. So we're actually seeing different parts of the sun as we look at different wavelengths. Well, no talk on the sun or any star would be complete without the obligatory HR diagram. This Hertzsprung-Russell diagram is designed to give us insight into the nature of stars. And you can put any star in the galaxy on this plot. The y-axis is brightness, the x-axis is temperature, and you'll notice that there's kind of a diagonal line. Well, it's not a straight line exactly, but kind of a diagonal line that runs from upper left to lower right. This line is called the main sequence, and in the main sequence, all of the stars along that line, which is where stars spend the huge majority of their lifetime, are doing one thing in common, and that is fusing hydrogen into helium nuclei. Individual protons fusing, which is something that requires quantum physics to do. It can't happen in classical mechanics. And then eventually releasing gamma ray photons along the way and producing a helium nucleus of 2 protons and 2 neutrons. The other thing about the, I hope you can see my cursor here. The other thing about the main sequence is that there's a mass-luminosity relationship here, which means that the brighter the star, so you're up high on the brightness scale, the more massive it is. And the dimmer the star, the less massive it is. Massive stars don't live very long. There's so much gravity pushing in onto the core, creating huge temperatures that just make fusion reactions go super fast. So they can run through their fuel pretty quickly, maybe in 10 million years in some cases. That's a blink of an eye in the lifetime of the star. Down here, these small red dwarf stars, they don't have much gravity. There's not that much pressure pushing in, just enough to cause fusion. So their lifetimes may be in the many tens of billions of years. So if you want a planet where life has a chance to form, you don't want to be orbiting one of these stars up here. And the sun is a great example. Sun's lifetime is about 11 billion years, plenty of time for life to form and evolve. Look at a model of what we believe the interior of the sun looks like. And the pressures increase and temperatures increase towards the center. We get pressures and temperatures high enough for thermonuclear reactions to take place, this fusion of protons into helium nuclei. As you move outward, and that's called the core of this, and as you move outward into the next region, we have what's called a radiative zone. It's gamma ray photons that are emitted from the core of the sun through this proton-proton reaction that was developed in 1943, I think we discovered that. I'll remember the discovery in a moment. These gamma ray photons move out into the, I'm sorry?
We were just getting some clipping. Is that cleared up, Danny? Okay, thank you. I'm sorry, Lou.
That's okay. if animations are causing problems, I can go to the next slide and just talk to this one.
You're good.
Okay. Got it. So the middle region here is the radiative zone, and that's where gamma ray photons kind of bounce around through this process of Compton scattering off of free electrons. And they bounce around forever. On average, statistically on average, it takes one of these gamma ray photons about 100,000 years to make it through the radiative zone. So by the time it does that, things are cooling down as we move away from the center of the sun. And we get to a region where the most efficient way to transport heat is convection, called the convective zone. And so these photons kind of hitch a ride on atoms that are convecting and are carried to the surface. And at that point, it takes about 8 minutes and 20 seconds to reach the Earth. So that's the internal sun that we have modeled. Okay, here's my eclipse slide. I promised one, I'm delivering. This is an eclipse slide. Here, the moon covers the sun. The moon, of course, is 400 times smaller in diameter than the sun. It's also 400 times closer than the sun. And so it just covers the solar disk most of the time. And when it does, when the bright photosphere of the sun is blocked out, we can start to see the tenuous atmosphere of the sun, the corona. And look at this. You can see structure. You can see structure in the corona. See these lines here? This structure is prima facie evidence of the existence of a solar magnetic field. These are plasmas that are attracted to magnetic field lines around the sun. And so they're glowing, they're incandescent. And so they are attracted to field lines, and we see their structure when we can blot out the very bright photosphere. Here are some really cool animations of the sun taken by the Solar Dynamics Observatory spacecraft. This is showing what a dynamic star we have. You'll notice coronal mass. We just saw a coronal mass ejection material being blown off the sun. Here you see loops of electrified gas cycling around sunspot pairs. This is also evidence that sunspots are highly magnetic. And so this gas is pushed off the surface of the sun, and some of it falls back because of the sun's gravity and also because of the localized magnetic fields of the sun. And if it's propelled fast enough, it actually escapes and goes out into the interplanetary medium, sometimes headed towards Earth. Here's some more SDO. By the way, these are in ultraviolet light. More SDO images of the sun. You see, again, the characteristic loops of plasma telling us that there are very strong magnetic fields here. And eruptions. This is like solar rain coming from one sunspot up, following magnetic field lines and down back into the sun. So I told you it's about magnetic fields, and you can demonstrate this yourself if you have a bar magnet and some iron filings. Here's a picture of one, and you can see the same kind of loopy behavior, these iron filings attracted to magnetic field lines and creating these characteristic loops, just like we saw on the surface of the sun. So sunspots are magnetic, as we've said, but why? Well, the answer is that the sun rotates. Let's get through all of these here. The sun rotates, but it doesn't rotate at the same rate. It rotates faster at the equator than it does at the higher latitudes. And so as the sun rotates, it drags its global magnetic field around with it, rotating faster at the equator than the poles. And that magnetic field over time gets really kind of tangled up. And you might imagine if anyone knits out there or have ever seen a ball of yarn that's been kind of thrown into the closet, it's got all kinds of loops and strings and so on. And if you held it as a ball, you might notice one loop of yarn kind of peeking out above the rest and then going back down to wind in through the ball of yarn. And that's what a sunspot grouping is. It's the sun's global magnetic field peeking out over the photosphere. Another reason that we know that sunspots are highly magnetized is from something called Zeeman line splitting. This green chart over here is a picture of spectral lines as viewed in high magnetic field environments. And you see this splitting into three parts of these spectral lines. This is because of the strong magnetic field. And we see that when we look at the sun and when we look at sunspots. So another piece of evidence that that sunspots are highly magnetic. Well, we've already noticed that sunspots are dark. They're dark because they're cool. I mean, not cool like we think of cool, but relatively cool. The surface temperature of the sun is maybe 6,000 degrees Kelvin. Sunspots are maybe 3,000 or 4,000 degrees Kelvin. But because they're cooler, they look darker, and I'll explain that in just a moment. The reason they're cooler is this magnetic field around the sunspots is pushing down on this upwelling gas, remember the convective zone, trying to release heat from deeper regions in the sun, but the magnetic field of these sunspots pushes down on that. It doesn't let the heat rise in those areas. So those areas become cooler. And as a result of their localized magnetic field. So why are sunspots dark? Well, they're cooler. And it turns out that because of an equation called the Stefan-Boltzmann equation, a tiny drop in temperature produces a huge difference in brightness. And I am so sorry to do this to you guys, but I'm throwing up this equation. This is the kiss of death when you give a presentation. So I'm apologizing ahead of time. L is luminosity, it's just brightness. 4 is a number, pi is a number, R is a number. And sigma t to the fourth, sigma is just a number. That's the Stefan-Boltzmann constant. So those are just numbers. But when you raise temperature to the fourth power, a tiny change in temperature produces a huge change over here in luminosity or brightness. So that's why sunspots are dark. You can kill me later. But it turns out that the sun is somewhat brighter actually during sunspot maximum. Now, this doesn't make a lot of sense, does it? Because there are more sunspots, and the sunspots are dark. So you might ask, why? Why? Faculae. I thought of that myself. It's my little. As the gas is trying to upwell, it can't underneath the magnetic field of these sunspots, so it moves around, it's compressed, and it moves up to the outer regions of the sunspot and produces brighter regions on the surface of the sun. And that's why. The sun has a sunspot cycle. There are actually a number of cycles. The most prominent one is the 11-year sunspot cycle, right? This has been known pretty much ever since not ever since we've seen sunspots. That's been 400 years. But for about 150 years, we've been able to characterize this rise and fall in the number of sunspots. And you can see that down here in the very bottom chart from 1900 to about the year 2000. It's kind of an old chart. You see a periodic rise and fall of the number of sunspots on the sun. You just count them. This plot in the upper right here, this black plot, right here. That is not our sun at all. That is another star. Other stars have sunspots and they have sunspot cycles. And so as we study our sun, our nearest star, the sun, we can better understand other stars and vice versa. Just another little plots of sunspot cycles over a longer period of time. You can see back in the 1600s, essentially no sunspots. That was called the Maunder minimum. And that was a period of time where there were very few, if any, sunspots on the sun. A real mystery still. It was correlated with a mini ice age in Northern Europe. And it was thought for a while that perhaps this lack of sunspot activity had something to do with this mini ice age. I think that theory has been discredited now. But if you look back into the late 1600s, you'll see lots of art, literature, and so on of very cold things, cold paintings of cold scenes, and books like Hans Brinker and the Golden Skates, or is it Silver Skates, that kind of thing. Another way to depict sunspots. Sunspots come in pairs frequently, and as you know, any magnet has a north and south pole, right? And so then I forget which one is which, but let's say the blue here is the North Pole, and this yellow is South Pole. And this is just following the sun over half of a sunspot cycle, roughly 5.5 years. And so we start off with lots of sunspots on the sun, and as time goes on, we're going towards solar minimum. We get fewer and fewer, starting out at solar maximum and going to solar minimum. This is real data from Doppler measurements of sunspot activity. So we go from initial observations of sunspots to a real understanding of the sun as a dynamic star that has cycles, it has storms, it has a field of influence called the heliosphere that we all exist in. Our Earth orbits in the atmosphere of the sun, the heliosphere. And a lot of these measurements that we've made and our understandings have been because we've been able to launch spacecraft that can not only see clearer, but can see in wavelengths that are blocked by our atmosphere, especially the high energy wavelengths, X-rays and ultraviolet, that don't penetrate to the ground much. Oh, I already did this one. I didn't get the slide here. Okay. This is a ground-based solar image of a sunspot. You can see a few things. You see there's a lot of convective activity, a lot of dynamical activity here on the sunspot. These cells of convective gas. It's like the surface of the sun is boiling as it's trying to release its heat. And you can see also very clearly the structure of the sunspot that we already talked about, the dark center, which is the coolest part, and then warmer outer portion. Dark center is the umbra, the outer portion being. As I mentioned, our sun is a star, and other stars have sunspots. We can see them now with, I think it's a speckle interferometry technique. But in either event, we can get some low resolution images of other stars at this point with our technology. This is Betelgeuse, which appears to have a very large sunspot on it. Betelgeuse has been in the news, of course, because of its brightening behavior, and as a red supergiant, we're all wondering when it's going to, explode and end its lifetime, and we don't know. But the point is that other stars have sunspots, and other stars have sunspot cycles. An image of the solar wind. sun is always trying to incorporate with its surroundings. And this is from the Whisper instrument on the Parker Solar Probe spacecraft. These highest resolution images that we have, these are particles, neutral as well as plasma, charged particles streaming out from the sun at very high velocities. And I wanted to just say a word about the discoverers of the solar wind. Eugene Parker theorized the existence of the solar wind back in the 1950s. He looked at the temperature of the corona, which was very hot, and said, you know, at those temperatures, you ought to be seeing particles streaming off the sun, you know, because these temperatures are exciting these particles to very high energies, high velocities. And he was largely criticized for this. But in 1960, Marcia Neubauer was I think she was the primary investigator on Mariner 2 plasma wave instrument headed for Venus. And that instrument observed the solar wind. And so when NASA built its latest spacecraft sent to the sun, they named it after Eugene Parker. Generally, you don't do that until a person has died. But Eugene Parker was alive and down at Kennedy Space Center to watch the launch of the mission named after him. And we'll be talking about Parker Solar Probe a little more in a few moments. Well, I mentioned we live in the atmosphere of the sun. Here's a graphic. Actually, I think this is supposed to animate, but showing the sun and many of the planetary orbits. This larger blue circle is, I believe, the orbit of Pluto. So you get a sense for how large the heliosphere is, the field of electrically and magnetically charged particles that emanate from the sun and define our fields and particles environment that we live in. The heliosphere has a boundary, and that is because as it pushes outward from the sun, the pressure of the solar wind gets less and less and less and less until it just balances versus the pressure of interstellar winds from other stars. And this boundary it's probably not symmetric. We don't think it's symmetrical like a sphere, but it does surround us. And its boundary is something like 130 to 150 AU away, right? 130 to 150 times the distance from the sun to the Earth. And the two Voyager spacecraft, which began as planetary missions to explore the outer solar system, are now through the heliopause, the boundary between the heliosphere generated by the sun and interstellar winds. And these two spacecraft are now in true interstellar space, each one with, well, one has 4, one has 5 fields and particles instruments, still sending back data after almost 50 years in space. Quite an achievement, and we're hoping to keep them going until the year 2027, which would be its 50th anniversary. So stay tuned for that.
Wow.
It has solar storms, coronal mass ejections, and just huge outbursts of particles and radiation. Here we see the sun not covered by the moon, but covered by a mask here that is on an instrument, a spacecraft in space, looking at the sun, blocking out the photosphere, which would be this white circle. And so now we can see, again, the tenuous gases coming out from the sun, these massive bursts of electrified gas called coronal mass ejections. Sorry, I got a few duplicate slides here. Well, the solar wind and the solar storms carry with them charged particles. And these charged particles, because they're moving, carry with them some of the sun's magnetic field. So that magnetic field from the sun is pushing outward and collides with our Earth's global magnetic field, our magnetosphere. And our magnetosphere gives way a little bit, but generally protects us and our atmosphere from the solar wind. And this is a model of what that interaction looks like. Our magnetosphere is important because without it, the solar wind particles would be knocking off our atmosphere in little pieces like billiard balls. And over millions and billions of years, our atmosphere would erode, we believe, in the same way that Mars' atmosphere has been eroded with data from the MAVEN spacecraft orbiting Mars, showing us how the Martian atmosphere has leaked into space as a result of the solar wind erosion. So lucky for us, we still have a magnetic field. These solar storms can cause beautiful aurora. They happen concurrently in the northern hemisphere and the southern hemisphere. In the northern hemisphere, they're called aurora borealis. Sorry, had a aurora borealis. In the southern hemisphere, they're called aurora australis. And the same physics happens at the same time for both regions. This is actually a picture that came from a trip I was on, gosh, 15 years ago, I think, in Barrow, Alaska, the northernmost point of North America. We can see these aurora from space. This is, I believe this is a space shuttle image, which had a fairly high inclination orbit, showing the aurora that's created by particles in the Earth's magnetic field, streaming in along closed magnetic field lines and slamming into nitrogen and oxygen atoms in the atmosphere, causing those atoms to glow. Here's another way to look at it. This is a graphic from real data of the auroral region around the pole of the Earth. And so just another way to look at auroras. And not just the Earth, but other planets have aurora as well. These are two images superimposed. One is a visible image. I believe these are both, excuse me, I believe these are both Hubble Space Telescope images. The visible image is of the whole Jupiter planet. And the two boxes are ultraviolet images of the poles. Jupiter's aurora are generated in very much the same way as Earth's aurora, particles streaming in and colliding with its atmosphere. But because we have different particles and different atmospheric constituents, we see these aurora predominantly in the ultraviolet. Saturn, too, has observable aurora at its poles. Both Jupiter and Saturn have massive magnetic fields, and they also interact with the the solar wind and the solar plasma environment. So who cares? I mean, okay, this is kind of interesting, I guess, if you have nothing to do late at night. But one of the reasons, the big reason that we care, is that these solar storms that come out from the sun largely during periods of high sunspot activity are force 5 events. And they have major impacts here on Earth and in space around us. Oh my God.
They said no, they can't hear and they can't see. It's still frozen. So
Okay. Can people hear me now?
Scott Richardson said it's still frozen. Can you
Okay.
hear him? I just came back. We're getting it. Okay. So should we go back to that other slide? I hate to ask you to
Sure,
do,
sure, sure.
that would be.
This
Thank you.
was the last slide, we think, that people
Yes.
saw.
Okay.
Okay. So the question was, why do we care about the sun? Why study the sun? And it turns out that in all field of astronomy and space science, with the exception of near-Earth asteroids, which could really cause a bad day for us, space weather, heliophysics, the study of the sun and its interactions with the solar system, is the only other field that has a real impact on our daily lives. And most of the time, we're not aware of it. These solar storms are force 5 events. They're very powerful events that slam into our magnetosphere, causing radio blackouts in radio communications, satellite operations, pose a real threat to astronauts' health in space, and can black out power systems, whole electrical power grids, because of the electric, the ground currents that get generated from the movement of the Earth's magnetic field. So we need to know about space weather, the study of the sun's solar wind and how it interacts with the Earth, the Earth's upper atmosphere, the Earth's magnetic field. And every nation on Earth that has the technology to do so monitors the sun, monitors sunspots, monitors solar activity in space, because it can be a real problem if you have your, imagine having your defense satellites taken out. That's not a good thing. There have been a few solar storms in the somewhat recent past that are of note. The Bastille Day storm back in 2000 was such a storm, and it had a major impact on a number of spacecraft. These are spacecraft from NASA and NOAA that were willing to report the impact that the solar storm had on their operations, on their instrumentation. Commercial groups, communication satellites, defense satellites are not as eager to report the status of their spacecraft. So we don't have those. But there has been a study done, at least one. Jim Green and Sten Odenwald at Goddard Space Flight Center did a study to see what would happen if a major solar storm hit. And I'm going to show you a major solar storm in just a moment. And the result was billions and billions, of course, in dollars of cost. In 1989, there was a solar storm that blacked out a good portion of Quebec for 9 hours. People were trapped in elevators and the whole bit because these ground currents that are generated by the Earth's wobbling magnetic field took out power grids in Quebec. Well, what I wanted to emphasize was that in 1859, the mother of all solar storms happened. We didn't have sensitive electronics. We weren't monitoring the sun that closely, but we had aurora. And newspapers all over the world reported aurora as far south as South America. So we know this was a massive solar storm. In addition, teletype operators reported that their teletype keys were fused together from these ground currents, and that they were, in some cases, blown off their stools by these electrical currents. So the study I just mentioned, James Green and Sten Odenwald, was modeled after this 1859 superstorm. What would happen if we had another one of these? And the economic impact alone would be devastating. Solar storms also pose a hazard to astronauts in space. And although we haven't seen a major problem with solar storms with our astronauts in the space shuttle or the ISS, back in the Apollo days, I think it was between Apollo 16 and Apollo 17, so nobody's flying at that moment, there was a major solar storm directed right at the Earth. And if astronauts had either been on the moon without a protective magnetic field, without a protective atmosphere, or in transit to or from the moon, it could have been a real problem for their health. So that's something that doesn't make any sense. It's counterintuitive. We are trying to figure out what is accelerating the solar wind. The solar wind kind of blasts out from the sun on a regular basis at, 400, 500, 600, 700 maybe kilometers per hour. This is really fast. And so,
Okay, we're getting 2 people saying that there's no sound.
oh boy.
Now we have sound. Okay. Don't know.
Should I go back to
How about just the last slide? It was only the last slide that they reported it.
okay. Let's go here. Okay. So these coronal mass ejections have particles coming out from the sun at up to 2,000 kilometers per second. And they can be a real problem to astronaut health. And back in the 1970s, although we didn't have anyone going to the moon at that time, between Apollo 16 and 17, there was such a solar storm. Fortunately, we did not have astronauts in space, but that storm was headed right to us. And if there had been astronauts on the moon or in transit, that would have been a problem. So with all of this, with all of our technology and all of our many decades of observing and exploring the sun, we still have some questions. One is, why does the sun's temperature, the temperature of the corona, increase as you move away from the sun? That makes no sense at all. The surface of the sun is about 6,000 degrees Kelvin. The temperature of the corona can reach up to a few million degrees Kelvin. We're not sure why. We have some thoughts. The second is, what is accelerating the solar wind? The solar wind is traveling outward from the sun at about 400 to 600 or so kilometers per second. Really fast. Starting to get into relativistic speeds here. What is the mechanism that accelerates these particles to such enormous speeds? And finally, what is the mechanism that accelerates these solar storms, these coronal mass ejections of energetic particles to the Earth? To find out, NASA and ESA and other countries have launched an armada of spacecraft to look at the sun, to look at the interplanetary magnetic and electric field environment, the heliosphere, to look at the Earth's magnetosphere and how it reacts to the sun, to look at the Earth's upper atmosphere, its ionosphere, to look at all those interactions and couplings. And this is a sampling, pretty good sampling, of many of those spacecraft that are, let's see, are these keeps this sun shield pointed at the sun, between the sun and its instruments. This is the Parker Solar Probe. So again, it was launched in 2018. It turns out it's actually a bit of a challenge to go to the inner solar system because you have to slow down rather than speed up. And this is just showing its orbital trajectory as it makes a number of passes to the sun, each one closer and closer and closer, and then goes out to around the orbit of Venus to transmit its data. And here we see an animation of the probe keeping that sun shield closer and between the instruments and the sun. I can play this one more time. Launching from Earth and making successive orbits out to the orbit of Venus and then back into closer and closer to the sun till it gets within about a little less than 10 solar radii. One of the things that Parker Solar Probe has discovered are what's a phenomenon called switchbacks. And this is these are solar plasmas streaming out from the sun that produce this kind of little S shape. And it turns out that it appears that this has something to do with the different speeds of the solar wind from different parts of the sun's atmosphere. And so you have this variable speed solar wind that engages in something called magnetic reconnection between open and closed parts of the sun's magnetic field. And they kind of interact together to create this S-shaped field line and carry energy out into the corona. So this may be one of the mechanisms that heats the corona. And this is just a kind of a graphic explaining with a little more detail what I just said. This is another image from the stereo spacecraft. These two spacecraft that were able to, for a while they were both working, view the sun in its entirety, front and back, showing a coronal mass ejection coming out from the sun. Just another piece of data that these events are very powerful. And I'll just end with I guess the Parker Solar Probe team produced their findings originally back in, I think this was 2022, I'm sorry, in Physics Today. And so you can find this online, I believe, where they've published a number of their results showing the images from the WHISPER instrument and verifying the solar wind, actually some images of Venus, believe it or not, as well as some of the discoveries of things like alpha waves and these switchbacks. So I think that's my last slide. Yeah. Oh, except for the URL. So I'll stop there. And I know I've said an awful lot, but perhaps you have some questions, and I'm glad to take your questions.
Going along, and unless you want to say more, is how do we see sunspots or star spots on other stars? What kind of techniques are they using?
I think
This is a YouTube thing. Like, YouTube is not working. Because that's what drops. So, okay, we should be back again. All right. So, I am not sure how long this connection is going to last.
Mm-hmm.
So, it looks like the problem is on YouTube's end, because everything is fine except the YouTube screen keeps going away. So
every time we lose it, we're losing people.
Yeah.
That's the other thing.
If your club members have questions,
okay,
and they want to email you, you can send them to me and I'll answer them.
Yeah. I will be glad to do that. We will not share your particular email necessarily.
Right.
So that way you don't get screened, but we can do that. We can do that, Lou. I'm sorry. Technology, some nights you have to understand, it's like we've had windstorms, haven't we, Danny, that have affected our connections. We've had we've had thunderstorms, you know, severe storms, we've had ice, you know, so I was
I
hoping
know, I
tonight
know.
that the storms are not supposed to move into us tonight until sometime early morning, probably 4 to 10 o'clock in the morning. But for a while I was worried, and so didn't think about YouTube having a problem.
Yeah.
So,
All this and Starlink too. It's just too much to take.
yeah, for sure, for sure. We'll blame Starlink. We'll blame global warming. Yeah.
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 Okay, same thing. But thank you so much. And here come some other people. Let's see. Yeah, somebody said probably due to the sun.
Mm-hmm.
No doubt.
Mm-hmm.
I think they must be here. Whoever's back on is either they're hearing or they're chatting among themselves. And we're getting people back again. It's just going crazy. Some of them are restarting.
Yeah.
And so
Yeah. So,
okay, I will tell people what to do. Okay, so
Yeah.
Danny, I'll let you, I'm gonna enter
Okay.
information.
Great. And hey, thank you again, Lou. I'm sorry that towards the end it got kind of wonky. I'm sure that other people have lots of questions, but if you have a question, make sure to type it into chat, and me or Eileen will make sure that you get a response from Lou.
Yeah.
But hey, all through your presentation, chat was full of "this is great. This is the
Oh,
most
good.
I've learned
Oh, yeah,
about the sun in forever." So thank you so much for doing this. This was great.
My pleasure. My pleasure.
And we usually have a gift that we give to our speakers. I am not sure how I can teleport one to you, but we will get that sorted out.
Well, I have something that I would like to get you, Lou, because I've done this for people who go out of their way to help us, especially we were doing this as COVID was ending, and then we finally came back in person and we were doing well, and then we've had museum issues. But what size are you? Because we have some Okie-Tex Star Party t-shirts, and last year's is awesome. We even reordered them, and I'm pretty sure we still have some. So
Oh,
what
that would be
size do you
great.
take?
A
Yeah.
large?
Okay, all right.
Yeah.
And it's red and it is beautiful. It has the Horsehead Nebula on it, and it was last year's. And this year we're voting on which one we are going to take, because this is our 40th year.
Mm-hmm.
So
Of the
Mm-hmm.
club?
of
Your
the Star
anniversary?
Party.
Of the
Of
Star
the
Party.
Star
Oh, the Star Party. Oh,
Yeah.
fantastic.
Yeah.
Yeah, the club's been going longer, you know, probably longer than that. So yeah.
The other thing that your audience can do if they want, the YouTube show that I'm on, Space Oddities, is a live show, and we take questions from the audience in real
Yes.
time. So that's another way that they can get to me.
Okay.
Mondays at
I
3
will-
o'clock Eastern.
We will share that. We will share that. So, but you know, a lot of what we're getting in the chat right now is lots of compliments. So, and people are saying they've learned more about the sun in this presentation than reading all the articles and textbooks, and they have an appreciation, you know, a bigger appreciation. So,
For
yeah.
sure.
It's great to hear.
And I have a question, and maybe I should save this, but what's the understanding right now and explanation of why, as you move farther out in the corona, it's hotter? What's the basic understanding right now? I know there's still more work to come, but
I think the explanation is that they're going with now is something called Alfvén waves, Alfven, named after Hans Alfvén. He won a Nobel Prize for this in 1970, I think. And so essentially you have this bulk transport of this magnetized plasma from deep inside the sun. And it because it's moving electric charge, it has a magnetic field associated with it, and it disturbs the sun's magnetic field. And so that creates these waves that carry large amounts of energy from within the sun into the sun's upper atmosphere, and they kind of deposit their energy in the corona. And so I think that's the physical process that we're going with now. That it's largely alpha waves.
That's a fascinating idea because what I'm thinking as a teacher, kids would expect as things move away from the sun to get cooler. So if you presented this is a great example of disequilibration because it's going to make the students go, what? Huh? That doesn't make sense, and so it generates a lot of discussion and then pushing them to the idea of what alpha waves are. That would be great.
I'm not sure anybody understands alpha waves. So if your students do, that's great.
But no, it's just that, they would try and sometimes we do what we call a CER, a claim evidence reasoning. And so you could present that as, what's happening. And they'd have to, there's your claim, and then they'd have to come up with evidence and reasoning to support or refute it. And
how old are your students?
Well, I was going to say, I would do this with, my high school students, but it would.
And the other thing is that NASA Goddard Space Flight Center is the center of excellence for heliophysics.
Right.
NASA. And so they have a space weather prediction center at Goddard, and they have a heliophysics branch that is got some really talented people in it.
I think I have met a few of them. They are awesome because I was there in 2018 with you when Parker was launching.
You might have met Eric Christian or Yari Colada Vega.
Yeah, I think so.
Or Mona Kessel, who's retired now. But yeah,
that'd be good.
Great.
Thank you.
You're welcome.
We just have all sorts of people, but sometimes kids think certain things should be a certain way, and when it's not, it blows their mind, and that's a good way to blow their minds.
It's not
frustrate them, but
just kids.
Yeah, for sure.
Solar scientists. Where have you been?
Danny's our IT, specialist too. And and I have to tell you, we have problems even when we're at the museum, but we think we've gotten them solved recently. They wouldn't let us on their Wi-Fi and they shut theirs down after a certain time of night. So it's created problems when we have to have we have anybody who is presenting and they're someplace else.
So we are back up now, but I don't know for how long. So I think I'm just going to call it here. I appreciate everybody for sticking with us through whatever was going on. Thank you for Lou. That was truly a great talk, and I'm sorry that we had issues for you as well.
Is it recorded on Zoom?
We will see what I get.
Okay.
Yeah.
Because he may be able to edit it.
Yeah.
Edit those parts out.
I think we'll be okay. So I think we'll be okay. But before we go, I wanted to tell you guys about, or show you guys a few things, in case you're